Okay, so today we'll go with this. Actually, weak constraint is something that we were left over from ASP, but probably I'm not going to talk about this today. We'll talk later when we actually need it. So today we'll start a new part, which is about reasoning about actions. And I put the lecture note on the blackboard, same as what you did for the other part in ASP before. So we'll refer to the lecture note, and the slides are made from that note. And so if you want to know more precise notations that are being used, you can refer to the lecture note. As well as there are also exercise problems. Your next homework will be assigned from that those problems. Okay, so we'll talk about today how the reasoning about actions and especially describing transition systems can be done in ASP. Some of your project that I know already involve certain changes in the state. So if you are doing some planning or specification of some workflow or some game playing, those involve certain changes of the actions, changes of the state according to the actions. And so this material will be relevant for those projects as well as for the general class. So what we are doing is, after we cover this ASP, we go into the reasoning about actions. Now this area itself is actually a huge area, and of course we don't have much time to do. So what we are going to do is to focus on more aligned with answer programming, so that you don't actually need to learn new languages. So what is this idea? So the field here is to be concerned with developing some formalism to describe the properties of actions. So the actions actually affect the state. So how you want to make those state changes to achieve certain goals. Or if you do certain actions, how those states will evolve. How can you predict what will come out of these state changes? Okay, so those are what is concerned. And when you talk about actions, this is a very general concept. So it's about anything that actually can be executed and may change the state of the world. In AI, the typical thing is about robot walking to some locations, or you can say about buying an item is also an action that affects the amount of money and the items being sold. Shooting a turkey actually has a historic reason. There's actually a famous problem involved with this called Yale shooting problem. We'll talk about that today. Or you can talk about network, communication network. When you send a signal or message in the network, that also affects the state of the world. Or if you work on the biology domain, there's also ligand binding to a receptor that changes the behavior of the cells and the organism. So we'll look at from the very simple problem. For instance, one of them is monkey and bananas problem. The picture was actually drawn by my friends Ezra Odem, who is actually a well-known cognitive robotics scientist. So here the problem is there's a monkey, and the monkey wants to grasp bananas hanging from the ceiling. It's a very typical, well-known example in psychology, right? You can also attribute to AI. So the typical solution is walking. The monkey walks to the location of the box and push the box under the bananas and climb on it and grasp bananas. Okay. So how do we solve this problem? Did we actually discuss this example before? Okay. So this is a standard example, but like getting to the airport example that we talked before, there's actually no guarantee that this plan will be successful, because we actually use a lot of assumptions that the box will not move when the monkey is walking to the box. Who knows that the box is remotely controlled, so when the monkey walks to the box and the box disappears, then the plan is not successful. Or whether the box is actually too heavy so that the monkey may not move, okay, so then the plan is also not successful. And also if the monkey climbs on the box and then the box collapses, then it also does not work. So there are many exceptions to this plan. Despite that, humans actually can make certain plan, which is a feasible plan. Basically, in this domain, monkey is the only one that moves. Box may be movable, and those kind of reasonable assumptions that human can make, even without actually the human knows the details. Okay, but we're actually good at those elaborations. If we are told that it's too heavy, then we can retract our assumptions. Okay, or if the monkey is smart to use a tool, then it can move. Okay, so everything is actually possible here. Okay, something that is possible if you talk to the elementary school students, grade level students. What they do is, actually I don't know where they get this idea. There is a machine gun inside the box, so that you can. I don't like that example, but the thing is, sometimes the plan that looks like unlikely is also can be viewed as a plan. One of the plan is actually one monkey goes to L2 under the bananas and wait until the banana drops down. Okay, so. All right, so now we want to formalize what is reasonable assumptions about this domain. So this is actually what we are going to see probably today. Now, there's another kind of the work like missionaries and cannibals problem, and I think actually we can play with this example. Okay, and if the missionaries are outnumbered by cannibals, they will be eaten. Okay, so if you do things like so this will be eaten. Okay, right. All right. So how do we solve this problem? Anyone? Let's actually do this like before. Can you take turns from the rows? Okay, from that row, from Arindam's row. Okay, so what is the first? Two cannibals first. Okay. Okay, and one of them should be out, right? That's reasonable, and one has to come back. Otherwise, there's no progress, right? Okay, so one in front. Argos row. One missionaries and one cannibal. Are you sure about that? No. Okay, so who else? Two missionaries. Two cannibals. Two missionaries. Whoever. Cannibal? Okay. Two cannibal. And of course, one of them has to get out, otherwise there's no point of progressing. Okay, so good, because now the... Oops. Yeah, no problem. Okay, so what shall we do now? Two missionaries? Are you sure about that? No? No? Who said no? Okay, raise your voice. Two missionaries. Are you sure about that?
Yes.
Okay, two missionaries. Okay, good. Okay, what shall we do? Two cannibals? Are you sure about that? One cannibal? Okay, so the thing is split.
Right? If the missionary stays in the boat, he won't get eaten. Is that right?
Missionary stays either side of the bank. If it is outnumbered, then they will be eaten. One missionary go? Are you sure about that? This guy goes, then he will be eaten by the two. Two cannibals? Then he will be eaten. One cannibal, one missionary? Okay, that seems to be fair. Okay, now what? Two missionaries. Wow. Okay. So then all the missionaries are in the place. Okay, what shall we do? Then cannibal can go. Yeah. Okay, from then on, you see the idea, right? In fact, the minimal plan here is actually 11-step plan. Okay. So everybody is happy after this. Bravo. Okay. So this seems to be a bit more difficult than the monkey and bananas problem, because it seems there's a more combinatorial search that is going on. In fact, this is actually easier in terms of solving by computer. Okay, because it's actually so clear. Okay, when something moves, the constraint is actually very clear about it. But in the monkey and bananas problem, this was actually not. Okay, so we're going to talk about this, and unfortunately we don't have time to go over all the wonderful development in this area. I just want to mention that this is called action description languages, which are about the formalism to describe the effects of actions, and they define transition systems. Basically, this is a directed graph, and the vertices correspond to the states, and edges are labeled by actions. There are many action description languages. Strips is probably the oldest one, known in Fikes and Nielsen's seminal work in the robotics. The Shaky robot, the first robot in AI, or the reasonable AI robot, was using this language. There's also other languages like ADL. Situation calculus is probably the textbook example of this. You probably have seen it if you took some intro to AI or graduate level intro to AI. You may have seen this formalism. There's also other formalism like event calculus, temporal action logics, language A, language C+, and so on and so forth. Okay. Now, we are not going to go all of them. In fact, actually none of them, but we'll talk about something in terms of ASP. Okay. All right. So, but actually the ingredient is actually the same. So, what is the basic requirement for this action description language? Right. So, this is a simple action description language that we'll focus on the first half of this class today. So, so here the transition system has only two states where P is true or false. So, P is something we call fluent. And fluent is something that changes when the time when action is applied. The value of fluent may change. Okay, so here P was false. In this case, so here P is false. But when action A is executed, then P becomes true. And when A is executed again, P still remains true. And also when A is not executed, denoted by this A equals false, the state does not change. Okay? So we are going to describe this transition system. But you can imagine in many practical examples, this is probably too simple. There are actually millions of states and maybe millions of edges in the real world. So this is some terminology. Fluence, as I just said, fluent is anything that depends on the state of the world. In the previous example, P was the fluent. Okay. Now, for other domains like monkey and bananas, whether the monkey has the bananas, is it true or false? Right? It depends on the state whether this fact can be true or maybe false. This is a fluent. Whether the monkey is on the box, this is also fluent. It's a true or false thing. There's also non-Boolean fluents, or sometimes called multi-valued fluent. The location of the monkey, so in the previous example, there were three locations, L1, L2, L3. So the values are not necessarily Boolean. Okay? The bananas, the box, their locations are also multi-valued. It's not necessarily true or false. Okay, so another terminology, the common sense law of inertia. So Newton's law of inertia is about that things will keep its current position when no force has been applied. And when you was not moving and no force applied, then the thing will stay there. That's Newton's law of inertia. Now, what we mean by common sense law of inertia is analogous to that. By default, the values of these fluents remain unchanged after executing actions. So for instance, when the monkey walks to the box stays the same because of the inertia. And the banana is also hanging in the same way. That's also by inertia. Okay? Now, if you look at the domain, there are actually a lot of things that is governed by inertia. When the monkey walks, the only change in the state of the world is the monkey's location. But all the other things, other objects' location remains the same as before. Okay, so that's according to the common sense law of inertia. Now, historically, this is actually one of the most difficult problems in AI. It's called the frame problem. How do we formalize the common sense law of inertia in some formal language? So how do we express so-called inertial fluent, meaning that the things are not affected by actions, they keep the same value as before. And this seems to be a very easy problem at first, but it turns out to be very difficult. And I will talk in the next page why this was so. Anyhow, this problem is actually solved now, and there are actually many solutions, and all the action description languages that you saw in the previous slide has good solutions for this problem. Okay, but just to illustrate what happened, this is a historic example. Yale shooting problem. It's about shooting the turkey. Although the original version was actually not about turkey, it's about a person called Fred, and people didn't like killing human, so it was changed into a turkey. Anyhow, the problem is let's say Fred is a turkey. He's initially alive, and the gun is initially unloaded. Loading the gun, waiting for a moment, and then shooting the gun at Fred is expected to kill Fred. So we want to teach computers to do this reasoning. Okay, just describing this fact. So the computers has to figure out that Fred will be dead at the end of these all events. So how do we do? So try to use logic. We want to say Fred is initially alive. We want to say that in terms of this alive of 0. So 0 represents timestamp. So it's a 0, 1, 2, how the time progress is there. Okay, and gun is initially unloaded. So how do we say that? Well, it's not loaded. Okay, so loaded of 0 means the gun is loaded. So negation of that means it's not loaded. And 0 means that initially the gun is unloaded. Okay, so loading the gun, and there's actually load of 0. Actually, I should say loading the gun. What to do? Now, if you load a gun, then the loaded becomes true. So here, what this rule is saying is, if the gun is loaded at time 0, then gun is loaded at time 1. Okay, so the load is an action, and loaded is a fluent. So when action or load is executed, then loaded becomes true at the next time. Okay. Now another thing is loaded and shoot. Okay. So again, I didn't write this action here, but let's say shoot is there. Okay. So in the story, the shoot was done at time 2. Okay. Because between time 1 and 2, you have to wait. So waiting means that you don't do any action. So shoot is done at time 2, and if shoot is done at time 2 when the gun was already loaded, then the turkey is not alive at time 3. Got it? Okay? Clear. On the other hand, this is actually wrong. So we want to derive this conclusion, okay, when so this story was represented in terms of the logical formula, right? This is what you already know. So remember what we did in the classical logic, propositional logic and first order logic. This is just simple first order logic, right? Okay. So what we want to say, this theory, when we give this to the computer, we want to say that this entails that Fred is not alive at time 3. We want to derive that. Yeah.
So loaded 1 and loaded 2, we say loaded 1 but never say loaded 2.
I said, can you repeat?
So you said what is wrong, so we said loaded 1 is
Oh,
true.
okay, you want to answer this question. Okay, so say that again.
So you said loaded, so we said that loaded 1 is true because we said load 0.
Mm-hmm.
But we never said loaded 2 is true. Like, nothing.
That's one thing, yes, true. Now, of course, you can actually test this with your standard knowledge in first order logic. It will not be entailed. One of the things that Arindam just mentioned is how do we know that loaded 2 is still true when loaded 1 was true? That's one thing. Another thing is actually about alive. Okay? So alive is 0 is true. How do we know that the turkey is still alive at time 1? We actually assume that turkey should be alive at time 1. But with this formalization, there is no guarantee that turkey will be alive at time 1. Okay? And in fact, it's also possible that turkey was not alive at time 1, but it can alive at time 2. Okay, that kind of thing may happen. Okay, so there's a lot of things that is not done here. Okay, so most of the problem here is if the action did not affect that fluent, the fluent should remain the same as before. That is actually not stated here. Okay, so I can easily say if I put like not alive 1, this is actually consistent. You can still say that Turkey is not alive at time 1, although there was no cause for that. Okay, and loaded 2 is still false, even if you expect that loaded 2 should be true after loaded 1 is true, but that is not guaranteed by this description. Okay. Now, of course, that was not the problem that AI suffered at the time. People already know how to solve some part of this problem. There were actually several formalisms available at that time. So in 1980, in the AI journal, there were 3 main formalisms to solve this kind of problem. Okay. Circumscription by McCarthy, Ray Wright's default logic, and also called non-monotonic logic by I think it was Drew McDermott's paper. Okay. Now this Yale shooting problem was given in a paper by Drew McDermott and his student, I think, the Hank. And what they said was the languages or the formalisms available at that time couldn't solve this simple problem. Okay? So what is this thing? The formalisms at that time has built upon the notion of minimal change, or so-called minimal models. Okay, so we talk about minimal models versus stable models before, right? So here's something that people try to think: how to solve this frame problem? Well, let's try to minimize the changes in the domain. Now, if you say alive 0 is true, okay, alive 0 becomes alive becomes false at time 1 is a change. Okay, let's not do that kind of models. Let's not look at those models. Let's minimize the change in the fluent. Okay, so we will only look at the models that minimize the changes. So for this example, let's only consider the models that minimize changes in the aliveness and loadedness. Okay, so that is the idea. I mean, the detailed formalism is actually much more complicated, but the essential idea is to prefer the models that minimize the changes. Okay? Now, according to that, this is one possibility. So, alive 0 and not loaded is actually true, because that's actually entailed by these 2. That's good. Now, I didn't show you here, but there was loaded at time 1, load action at time 1. There's also shoot action at time 2. Okay? So this change must happen because load 1 is true, and the load 0 actually. So we are trying to say load of 0, meaning that this action happens between time 0 and 1. Okay? So when load 0 is true and not loaded, loaded 0 is true, then loaded must become true. Why? Because of the third rule, right? Yeah, so this one is. So this is fine. This change is actually justified. Okay? Now, when shoot is executed, alive becomes false because this last rule says loaded 2 is true and shoot 2 is true, then alive 3 must be false. So if this is true and shoot is executed, then alive is false. So this change is also justified, right? And all other fluents should not change all other cases, the fluents should not change the value. So for instance, from alive 0 to alive 1 doesn't change. Alive 1 to alive 2 does not change because we didn't say the reason for that. If there is no reason, then it keeps the same value as before, same as all the other things. Okay, looks convincing? The problem with this approach is actually exactly from this domain, this example. Okay, so can you actually find out what is actually wrong with this idea? it looks fine for this case, right? And the formalisms available at that time was guaranteeing that alive 0 and alive was guaranteeing that okay, this one does not change, this one doesn't change. Okay, so these are all guaranteed by the criteria here, because we are only looking at the models that minimize the change.
So if load 0 never occurs, it's still satisfied?
In this problem, load 0 actually happened.
It does. Okay.
Yeah, so let's actually, that's what I added before. Let me do it again. So this is actually the two facts that I should have added before. So what is wrong with this? It's actually tricky, right? So the problem is there's actually another thing here, okay? So let me say, in addition to this, of course, load of 0 should be there and should of 2 is there. This is already there, okay? Let's look at the second scenario. What happened was the AI system that was based on this assumption was producing a second scenario. And in the second scenario, what happened was this. This load has to happen. This is justified, right? Now, there's actually another change here. Okay, so if you count the number of changes in the fluent, this model has 2 changes because of this guy and this guy, right? The fluent changes from false to true and true to false. Okay, there are 2 changes. Now, if you look at the second one, they also have 2 changes. Okay, from false to true, true to false. Now, what happens in should case? Now, should 2 is actually true. However, loaded becomes false. So this change is actually guaranteed because there is no change. According to the minimal change criteria, this is actually minimal change. You don't have to change when loaded was false, right? So if you only count the number of changes in the fluent, both of them are equal. They have only 2 changes in the scenarios. So if you interpret the second scenario, what happens is this. You load the gun at time 0, okay? And the gun is automatically unloaded. Why? Because to prevent alive to become false. You get it? In order to minimize the changes in the aliveness, the loaded actually changes one more time. So it creates 2 changes in the second scenario. And in terms of the model's perspective, minimal model perspective, these 2 are equally likely. Yes?
Also, like, if your minimal model, Lec0 and not Lec1, not Lec2, not Lec3.
Okay, say that again?
Lec0 is there, but not Lec1, not Lec2, not Lec3.
How about the loaded then?
Sorry?
How about the loaded?
Loaded was the original one, not loaded 0, loaded 1, loaded 2, loaded 3. So for the first 2 rows.
Wait, which scenario are you changing now?
I'm talking about that scenario which is represented with the first 2 rows.
First?
2 rows on the top.
Okay.
Alive 1.
So let's say, what do you think? Alive 0?
Alive, not alive 1.
Not alive 1.
Not alive 2.
Not alive 2.
Not alive 3.
Not alive 3.
Yeah. And not loaded 0.
Not loaded 0.
Loaded 1. Loaded 2, loaded 3.
Okay. Now load should happen here, right?
Yes.
And should happen here.
Yes.
Yeah. Okay, let's look at this. So there are actually 2 changes here. And loaded becomes, oh, okay. Yeah, I think for this domain, maybe that's also the case.
But it won't work, right? Because we already have a rule that alive to and an action should do is perform it goes to the not alive 3. Right?
Well, the should action depends on this one, right? So the load is true, should is true, alive is false. That is actually conforming to this rule, right? So there's nothing wrong with that. I think original description was saying that after the shoot, the gun is unloaded. So maybe that's another story that is missing from this. Okay. Okay, good. So the problem is there are some changes that is actually reasonable, some changes that are not reasonable. So just minimizing the changes actually doesn't work. Okay. Now it turns out that the formalisms available at that time, they can actually solve this problem. But the encoding is actually not very natural. So what the paper, this Yale shooting problem paper was claiming was the formalisms known at that time couldn't solve this simple reasoning problem, so there is no hope for AI to solve this problem. And then it becomes somehow coincide with AI winter. Okay, because AI cannot solve even this simple problem. Turns out later, people found out that there is actually a way to use those old formalism to solve this problem. It was actually a bit more complicated than the natural way, but there is actually a solution for that. Okay. However, what this paper influenced in the community was trying to see what is actually the better way to represent this knowledge. And this is actually what we are going to look at today. And you already know the solution. You just need to see how the solution looks like. Okay, so so let's try to look at this transition system. Okay, the common sense law of inertia is that A is false. When A is false, the state does not change. So how do we describe these loops? That's actually the frame problem. Okay. Now, how do we use ASP to solve this problem? So let's talk about a very simple case. We are interested in the histories of length 1. So we are looking at only one-step transition. Okay. And we will use following atoms. P of T0 means that the fluent P is true at time 0. And fluent P is false at time 0. And same for time 1. Actually, this should have been time 1. Okay, the typo. Okay, so, and there's also A, meaning that a action is executed. So we'll actually use this as a base for extending to histories of arbitrary length. So for now, we'll just look at times 0 and 1. Okay, so the very first thing is how do we describe the effects of executing this action? It can be described by this. So P of T1 if A of 0. Okay? Meaning that if A is true, action A is executed between time 0 and 1, then P becomes true at time 1. Are we together? Okay. Again, if we just write this rule, it does not solve the frame problem, and we'll encounter a lot of spurious models as we saw in this Yale shooting problem. So what do we need? We need to actually add more rules. What is missing is how do we determine the value of P in the initial state? Because this one by itself did not say anything about it. By the way, if you look at this rule only, what is the stable model?
Nothing.
No, nothing and empty
Empty.
set is different, right? So empty set is the stable model. Right? Empty set is the minimal model here, right? Okay. Now that doesn't say whether P is true or false at time 0. We need to have those possibilities. But the rule itself does not say anything about it. So we need a rule for that. Second one is how do we know that the A is executed or not? Because the empty set doesn't say anything about action. Actually, it means that you can interpret it as A is actually false. A was not executed. But we need to say that action can be executed. We also need to say how to determine the value of P in the next state if A is not executed. Okay? So A will keep its previous, P will keep the previous value. This rule itself does not say anything about it. We also need to say that exactly one of the atoms, P is true or P is false, should be, one of them should be true at any moment, time 0 or time 1. Okay? So what we are going to do is to add these 4 rules. And please pay attention to these 4 rules, because this rule will appear many times. Okay? In fact, when you change the domain to another one, like monkey and bananas and so on and so forth, the changed part is actually here. This rule will be actually kind of universal. These are domain-independent axioms that you're going to use. Okay? All right, so how do we determine the value of P in the initial state? It's actually very simple. Let's say that initial state can be arbitrary. Okay, because P can be true or false at time 0. How do we express this concept? By choice rule. Okay, so choose one. P equal P T comma so this atom or this atom. Choose exactly one of them. If you insert this to the previous rule, then now the stable model will say either P is true or false. There will be 2 stable models now, right? Do we get it? Okay. So now we solved the first problem. Easy. Now what it says in terms of the terminology, this P is called exogenous at time 0. What that means is that whichever cause determine the initial state is actually out of the theory. The theory itself allows both possibilities. Okay? So this is just terminology. Now, if you look at this one, it also covers the part of 4, which was actually only one of the value true or false holds for P at time 0. Okay? Because when you write this rule, it's already guaranteed. Okay? The next question, how do we determine whether action A is executed? Again, A can be executed or not executed. So in terms of the previous terminology, execution of A is exogenous. The theory itself does not direct yet. Okay? So it can be both possibilities. How do we represent that in ASP? Yeah. So just write this one. A of 0 is choice. Either A of 0 can be included in the stable model or not. That's it. Okay? Good. Now if you have those rules so far, how many stable models are there? 4. Because P can be true or false, A can be either executed. Okay, so there are 4 possible combinations. In fact, actually, that's not strictly true, but let's just glimpse for now. All right, so next thing is how do we determine the value of P in the final state when A is not executed? Knowing that this is actually the frame problem. Okay, this is the most difficult problem that haunted many years in computer science and in AI. We'll actually combine this with another, the other one. Exactly one of the atoms is true at time t. Okay, in fact, we already solved half of the problem, so we are going to look at only one case. Okay, instead of at any time t, we'll just look at exactly one of them should be true at time 1. The way that we do is this. Okay, so there are 3 rules that we add. Let's read the rule together. Okay, despite these simple 3 lines, it'll probably take some effort to understand what is going on. So, what this rule says: when P is true at time 0, then you can either choose to include that P t, 1 in the stable model or not. So this is a choice, right? Same for the false. When P was false, then you can either choose to include the Pf1, 1 in the stable model or not. There's a choice here. Okay? Now what is the next one? The next one is actually constraint. So it's kind of double negation here. Okay, so there's a double negation of negation. So what it says is actually a constraint saying that there is exactly one of them must be true at time 1. Okay? And these 3 lines are enough to solve the frame problem. So let's see what is going on. Now, so far, we described this, there were 5 lines here, okay? So, question, what will be the value of P at time 1 when A0 is true? If you say A0 is true, you write the fact that A0 is true, okay? Together with the all rules that you have seen. What will be the value of P at time 1?
True.
P will be true at time 1 because, why? A0 is true now, right? And we had the rule saying when A0 is true, then P of t comma 1 must be true. Okay? Good. Now the question. What will be the value of P at time 1 when A0 is false? Now the first rule that we saw doesn't apply here because A0 is false, so it doesn't do much about whether P is true at time 1, right? That rule is redundant. So, what will be the value of P at time 1?
Would be either true or false.
It seems it can be either true or false. It seems. Because this rule, the first rule here says, actually I should say P was, let's assume that P is true at time 0 for simplicity. Okay, let's choose it. This rule is saying that you can either choose to include this atom or not. Okay? Now suppose you include this atom. Okay? So that's one possibility. What happens? This is actually true, right? Because Pt comma 1 is true, but f comma 1 is not true. It's not derived yet. So this constraint is true. So that's actually good. Okay, let me repeat. So there are actually 2 possibilities. P can be true at time 1 and P can be true, false at time 1. Okay? So if P is true at time 1, that is actually explained. Now P is false at time 1, meaning that let's not choose this one. According to this rule, it says you can choose either to include Pt comma 1 in the stable model or not. Let's choose not to include this one. What will happen? This constraint will be violated because none of these atoms is derived. So it violates the constraint. So although this one looks like a choice rule, but because in the presence of this constraint, now it has to choose it. Okay? Let's actually look at also the other case. So let's assume that P is false. Okay? Now A is not executed. What will be the value of P at time 1? Again, this is a choice rule. If you do not choose to include Pf comma 1, then nothing will say about what will be the value of P at time 1. So this will violate this constraint. So in this case, when action A is not executed, then P of f comma 1 must be chosen. In other words, you can read it as a by default. When P is false, then P has to be false at time 1. Now with this default can be overridden if you say A0 is true, right? Because what happens in this case, so let's assume that F0 is already true and A0 is true. Okay? According to the first rule in the previous slide, what happens? You must have this one, right? Now what happens if you also choose this guy? Then it violates the constraint. So this choice will be retracted. Okay? So here is a simple way to read this formula. In the presence of this rule, each of these choices works like a default. By default, P is true at time 1 if P was true at time 0. And same for this one. Now this default can be overridden if there is a reason for defeat. When A was explicitly executed to change P to be true at time 1, then this default rule do not apply. Question?
What does P being true or false represent in the shooting problem?
In the shooting problem, there was a different action and different float.
So loading and loading.
Loading is an action, like A. Okay? And alive and loaded were fluent, like P here. Okay? Alright, so these rules are illustrate solution to the frame problem in the stable model semantics. Now, I know this may be a bit difficult to grasp in the first sight, so I have an exercise problem for you. Okay? Before we talk about that, let's actually just look at this again. Yeah, this is actually what I just described. The first rule says if the value of P is true at time 0, then decide arbitrarily whether to assert P is true at time 1. Now, if there's no other rules, no other information about P, then according to this description, you have to assert that P is true at time 1, not to violate the last constraint. Okay? But if you are given the conflicting information about the value of P at time 1, so if you say that A was true, which makes P true at time 1, that it conflicts with the fact that you choose P equals, let's say, false at time 1, if P was false before. Right? So then, in that case, you have to, you should not assert P F, 1. Actually, this should be F. Okay? Assuming that F was false at time 0. Okay? All right. So in order to know this in detail, I want some of you to volunteer for presenting this problem in the next class. What I ask you to do is look at these 5 lines program and find the stable models. How do we find stable models? By hand. You have to write the reduct and check the minimality. Okay? So you can now, of course, use Klingo to check it, but I want you to actually try this, and I hope some of you can volunteer for this presentation. So whoever present, write your solutions on the board before the class starts. What you need to do is to write the program, okay, and write each of the stable model, and you have to explain. So you write the reduct for each of the case. Okay. Second problem is actually typo, so ignore this. All right, question up to this part. Yes?
So the problems that we have to do, where do we find the
In the handout. These are all from the handout.
Oh,
Yes. Okay? Yes?
So if like for the exogenous variables, Pf0 and Pt0, if we say both of them are true, that will not be correct, but then it will have 2 stable models.
Both of them cannot be true because we have the rules that says you have to choose exactly one.
No, that is for time point only.
No, we have this one.
Okay.
Okay? So that was already solved before. All right, so now let's try to expand the timeline. So how do we actually reason about paths of length m? So we only look at the paths of length 1. In fact, actually, I should tell you how many paths of length 1 were there in this transition system. How many paths of length 1 in the transition system? There are 4. So P equals false, A equals false, and come back to P equals false. That's one-step transition. And P equals false, A equals true, P equals true. That's the second. P equals true, A equals false, P equals true. Okay? And P equals true, A equals true, P equals true. Okay? So if you look at the 4 stable models in problem 1, each of the 4 stable models will correspond to each of these transitions. Okay. All right, so we'll extend this. What we do is actually very simple. just adding timestamps to going from 0 to m. So m is kind of maximum step. Okay? So we'll have multiple atoms, p of t, 0, t, 1, t, 2, t, 3, to denote what is the value of p at those times. Okay? And again, a will have also the argument go from 0 to n minus 1. Why n minus 1? Because we understand the action is executed between time I and I plus 1. So it goes up to n minus 1. Okay? All right, so the value of p, t, I, f, I characterize the state Si, and AI represent the events executed between those two states. Okay, so how do we do? So we'll first introduce Boolean as a sort, true or false. Direct effect. Okay, so this is similar rule as you see before. The only change is instead of 0 and 1, I'm using t and t plus 1. So at time t, when A is executed, then p it becomes true at time t plus 1. Okay? And here t is going from 0 to n minus 1. Now m is a placeholder. You have to give the value when you call the Klingon. Okay, so how do you say initial state is exogenous? Same one. Instead of writing this rule that I showed you before, I'm using actually the local variable here. So B can be either true or false, and you have to choose exactly one atom. Okay? Uniqueness and existence of values at time other than 1. Other than 0 is represented by this rule. Here t goes from 1 to m. Okay? Now this rule and this rule are so much similar, right? But there is a critical difference. You cannot replace this one with this. Okay? And that's actually another exercise problem. If you delete this part, if you remove this guy, okay, what will happen? Okay? It will be actually incorrect. All right. The other thing is action executions are exogenous, so that is represented by this. Now t goes from 0 to n minus 1. Common sense law of inertia. Before we had two rules, but I can use this variable b for the Boolean variables. I can just change into one line. Okay. So whatever the value of b, it was the value of b at the time t, then the same value will be true at time t plus 1 by default. And if you don't want to see some other sort, you can only you want to only see this, those p and a, then you write this directive. Okay. So how do we find all states? You can actually, when you call this program by m equals 0, then it will return all states. So how many states are in this transition system? There are only two, p equals false or p equals true, right? So when you call this program with m equals 0, what happens is it returns all the states in the transition system. So that's what you see, p of f equals f comma 0. That's one stable model. P of t comma 0 is another stable model. Okay? So there are two stable models. Now if you call this thing with m equals 1, it will return all 4 transitions. Okay, so I told you there were 4 transitions, so let's look at this for instance. This one means p is true at time 0, and no action is executed because a does not appear here, and p is still true at time 1. Which edge is it? This stable model corresponds to which edge in the transition system? P equals true at time 0, A is not executed, and P is still true. This one. Okay, so this guy is this one, this edge. Okay, what about this guy? P is true, and A is executed, and P is still true. This one, right? And P, this one is this, and the last one, P is false. Now A is executed, and P becomes true. This is edge. So there are 4 transitions in this system, and each of the 4 can be returned as the stable model here. When you call this program with m equals 1. Now if you call m equals 2, then what will happen?
60.
When m equals 4, then it will try to find all the passes of length 2. Okay, so you can try that. All right, so here's a question that I just said. So in the case for time 1 to m, we use this constraint. While at time 0, we didn't write the constraint, right? We have write direct assertion. Now, what happens if you remove this if not? So just write this one like the one for the time 0. How will the stable model change? Okay, so this is what you can do, and you have to explain by hand. So this will be the second problem for class participation for next class. Okay, so this is actually problem 2 in the handout. Okay, any question up to this part? All right. All right, so we'll move to the monkey and bananas problem, and probably we will look at only half of it for today, maybe. So, knowing the previous simple transition system, we can actually extend to a larger one. So here, monkey and bananas. What are the states? In monkey and bananas problem, a state can be described by specifying each of these 3. What are the locations of monkey, bananas, and box? Okay, and whether the monkey is on the box or monkey is not on the box, or whether the monkey has the bananas or not. Okay, how many possible combinations here?
If the current locations are
3, L1, L2, L3 as in the picture, yes. How many possible assignment can be given here? There's not. How many?
Is banana always stable?
Hmm?
Is banana always stable?
Well, look at the thing, whether the bananas.
Or can?
So only look at the proposition written here. Whether the monkey is on the box or not, whether the monkey has the bananas or not, or the locations of each object. How many possibilities here?
This is not 27 multiplied by 2 multiplied by 2.
That's 108 states. Okay? So unlike the previous picture that I can show you the 2 states, now it becomes 108 states. Of course, not all of the states are actually valid. Okay? In fact, there are only 48 valid states in this picture. Now, why is this so? We'll try to describe a state in terms of these atoms. So we can write log of x comma L to denote location of monkey, bananas, and box, where the L, actually this one must be L, should be one of these values, L1, L2, L3. Okay? Now, it has bananas and on box are Boolean floats. Okay? Now, if you look at the interpretations, then obviously there are 108 valid interpretations, okay? Meaning that each object can belong to only one position. But there's also some other things. First of all, of course, each object has to have a location, and each object can occupy only one location. The second rule is saying there is no y and y1 such that x belongs to 2 different locations, y and y1. In other words, each object can belong to only one location. Now the other one is if the monkey has the bananas. Now the monkey has the bananas. What do you expect about the location of monkey and location of the bananas? They should be the same. So the next rule is saying that if the monkey has the bananas and monkey is at location L, then bananas should be also at the same location. So you cannot have the state where the monkey and bananas are at 2 different locations while the monkey has the bananas. Okay? Similarly, if the monkey is on the box, then the location of monkey and location of box should be the same. So you have to describe all these things to say that these are the valid state. Okay. Okay, good. So how do we describe this domain? So first, we have to declare source and object declarations. So there are there's a Boolean sort, which contains 2 elements, true and false. There's 3 objects, monkey, bananas, and box. And there are 3 locations, L1, L2, L3. Good. How do we describe the state constraint? Okay? So all you need to do is just to read these rules in English. Let me read it for you. If the monkey has the bananas, which means at time t, okay, this t means true, and this capital T is the timestamp. Okay? If the monkey has the bananas, and if the location of monkey is at L at time t, then the bananas are also at the same location L at the same time. Same way, if the monkey is on the box, and the box is at location L at time t, then the monkey is at L at time t. True? Okay. Then we describe effects and preconditions of this action. The first rule is saying if monkey walks to location L, then the monkey's location at time t plus 1 is L, the destination. That's effects of action. The next one is saying about when this walk action should not be executed. So here, this is a constraint. If the monkey is at L at time t, if the monkey is at L at time t, and monkey walks to the same destination, this does not happen. So in other words, we prohibit walking to the same location. Okay? The other one is monkey is on the box, then monkey cannot walk. Right? That's a reasonable assumption to make. Similarly, for the pushing the box, if the monkey pushed the box to location L, then the box is at L at time t plus 1. But now, not only the box, but also the location of monkey changes. So we need the second rule too. Right? Similarly as before, if the monkey is already at the destination, monkey cannot push the box to the same location. If the monkey is on the box, it cannot also push the box. Okay? We are not talking about acrobatic monkey here. Okay? Now, the last rule is new. So monkey is at L1 and box is at L2. They are two different locations. Then the monkey cannot push the box. It doesn't teletransport. Okay? That makes sense, right? Okay, good. The other actions are also similar. Monkey climb on, and so in fact, the monkey is on the box at time t plus 1. Now, of course, monkey cannot climb on but the monkey is already on the box. The next one is if the monkey and the box are at two different locations, then the monkey cannot climb on. If it tries to do that, it violates the constraint. As you see, each of the rules is actually a very natural thing to write and very succinctly written in ASP rules. Monkey climb off, then of course, next state, monkey is not on the box, represented by on box f, t plus 1. If the monkey is not on the box, of course, he cannot climb off. Grasp bananas is same. If monkey grasp bananas, it will have the bananas in the next time. But if monkey already has the bananas, it cannot grasp bananas. If the monkey is not on the box, it cannot grasp bananas. If the monkey and bananas are at two different locations, monkey cannot grasp bananas. Good. There are also some concurrent actions that we want to prohibit. We don't want to say monkey walks and pushing the box at the same time. Okay? We don't want to say that monkey walk and climb on at the same time. We don't want to say that monkey can climb on and pushing the box at the same time. Okay? And climb off and grasp bananas. It's like a jumping, but we don't want to say this kind of thing. It's actually up to you. If you want to say acrobatic monkey that does all these things, it's up to you. Okay, so this part are the domain dependent axioms. Previously, we write only one rule for the simple transient system. Okay? Now for the monkey and bananas, there's actually much more rules that we have to write. Now the second part is domain independent axioms, and this part remains almost same as the simple transient system example. So we have to say initially fluents are exogenous. How do we do that? Choose one from this atom. Choose one. Choose one. Okay? Uniqueness and existence of the fluents at time other than 0. This is similar to these rules, but we use constraint form. Again, this is same form. Actions are exogenous. We write these rules as a choice rules. So action can be executed or not. Common sense law of inertia. The default rule is written in this form. And again, this same form. Okay, the question, this is actually not for the class presentation. So class presentation problems are only the first two problems. You can actually check with Klingo by running the Klingo, how many states are there and how many transitions are there. Okay? All right, so I went through quickly about monkey and bananas domain, but there are actually a few things that need more explanation. So that's what I'm going to do next class. And in the remaining 4 minutes, I'm going to ask TA to come, and she will explain the grading criteria. And in the meantime, you can also write the exit ticket. Okay?